Hi. So yes, I'm Matt Davis. I studied electrical and computer engineering at the University of Illinois and graduated in 2008. This will be a three-part talk on embedded camera hacking. The first part will be on background and extraction of embedded device firmwares. We'll look into what firmwares are, what they contain, and what you can learn from them. The second part will look into Linux device driver development and reverse engineering closed drivers by leveraging modern day LLMs. And then in the third part, it was going to be about why not every embedded device should be automatically connected to the cloud services. I personally feel this way, that cloud services should be opt-in on any device. However, back in April, something much more interesting happened. Co-researcher Alfonso Gamboa and I got further in our secure boot research, and then I felt it had become materially relevant to replace the third topic with an actual pillar on secure boot implementations. The content should be interesting for a range of skill levels. We're going to move quickly through the slides to stay within limits and hopefully leave time for a bit of a demo at the end. So let's get started. Why security cameras? Back in 2006, I got hooked on Linux device drivers and Linux, the operating system, and device driver development. We read the second edition of this book under Professor Stephen Lumetta's course on Linux and device drivers. I then kind of took a long break. I found at the time that PIC microcontrollers were rather challenging to work with, and I focused after that entirely on software until around the time that the Raspberry Pico microcontrollers came out a few years back. What I found after that is that embedded security cameras are quite interesting. They carry far more complexity than their earlier analog counterparts did. IP cameras sit right at the intersection of Linux, hardware, digital signal processing. Sometimes, cameras like these will even have a neural chip built in that lets you do some basic AI and machine learning inference. With units like those starting at $10 to $15, they make an attractive research target. So what you get when you buy a camera like that is you have a full Linux system on a chip, video pipeline. They're connected by default with networking, and there's starting to be a trend towards using secure boot. Secure boot we'll discuss later in the talk, but vendors prevent you from running your own software on the camera by doing this. So what is firmware? What is a SOC? A SOC is a little different from the SOC we were talking about earlier today. This is a system on a chip, and here's an example. In the corner here in the center of the board is a chip that contains what you'd consider your CPU as well as your RAM, and any other hardware blocks that are specialized for the embedded device itself that, in this case, a camera. Next to it is a lens. Underneath the lens is a sensor. And the firmware is the persistent software that runs the device itself. It lives on flash chips. We'll show some of those in a minute, but the flash chip contains your bootloader, your kernel, and your root file system. They tend to be readable and modifiable and reflashable. It is possible to write protect flash chips. It's not as typical in these type of cameras. And it's what actually runs when you plug the thing in. So when we talk about firmwares, they're stored on a flash chip. You have NOR chips and you have NAND chips. They're not really the same, though they're conceptually similar. The NORs tend to be smaller, 8, 16, 32 meg chips. They don't contain bad blocks ever. What you read is kind of sequential, and that allows for using a file system like squashfs. NANDs, on the other hand, they get bad blocks, and bad blocks grow over time. And to deal with this, you end up needing a file system like UBI and UBIFS that's like one more layer of abstraction over the MTD. You don't have to understand all of that. Essentially, though, the flash chips can be read using probes and programmers similar to like what I'm holding in my hand. You'll see in the next slides some examples of using command line programs with such programmer to read the firmware. Snander is a typical program. There's also a fork of it called Scriba. These programs contain kind of a database of known flash chips, and your flash chip from your device should be in the database for you to be able to read it. Some other things to call out is these programmers. Here's a picture actually of this very laptop and this programmer hooked up to a camera. One thing to note is these things ship with some jumpers, and they'll kind of lie to you and say like, oh, if you put the jumper here, it'll be 3.3 volts. Usually not true. This one's been modified. I scraped the trace off the back side so that it was truly always is 3.3 volts. So if you go down this path, make sure you look into that, get a voltmeter, that kind of thing. There is a wiki on this Theano firmware project which contains additional information as well about using these type of programmers. Here's an example of using the command line program Scriba to read a firmware backup. You can see in the first attempt it didn't detect the flash chip. That's because these clips are kind of finicky. You have to have them perfectly aligned on the flash chip. If you do not, you'll not detect it. It's kind of a 4x speed on the read to give you an idea how long it takes over the clip method. So this video was sped up 4 times. Once you back up, you want to basically take a SHA hash of the backup and then back up again. So like in this example, you can see the hashes are different. You shouldn't trust that you have a good backup in that case. Always back up until you end up with the same hash, and now you can be sure that you have a consistent backup. The type of cameras that the Theano firmware has focused on are Ingeniec-based chips. They're a semiconductor manufacturer. Why these chips is they tend to have strong image quality. They appear in affordable hardware. You can find public FCC teardowns of the hardware to confirm before you buy a device what you expect the chips on it to contain. Like there are a lot of different SoC manufacturers out there, so not all of them support alternative firmwares. There's also this concept of USB extraction. The programmer is actually a serial programmer. USB extraction is a little bit different. That's when the SoC itself has a special mode, like a bootloader mode, that you can read the firmware using an alternative protocol. In this case, the Ingeniec devices have a cloner protocol. The cloner protocol, I won't talk too much about it other than to say that we learned some other information from this protocol as well, and we'll get to that later in the talk. Once you have extracted the firmware, you'll have a bin file, and you may be wondering what to do with it. Binwalk is your program for that. It lets you extract the contents of that firmware binary and look inside. So here's an example. Once it's extracted, you may use things like strings, find, grep, and just look around, you know. Like in this particular example, we see things like the app version, a get-SHA hash. There's a cloud profile INI on this device that had several vendor API endpoints. Some peer-to-peer streaming tokens as it relates to those networks. And then we also saw a squash FS file system mirrored twice in kind of an A/B mode. A lot of vendors will do this if they push firmware updates over the network. That way, if one of the firmware updates were to brick, there's a B side of the file system that can take over and try and repair for that. So this kind of brings us towards chapter 2. Chapter 1 was a lot about the layout and land of embedded devices and extracting firmware. On those chips are Linux device drivers. So what is a Linux driver? You'll typically have your application in user space memory. In this case, this is an example of looking at the actual image signal processor driver. So your streaming application on these Ngenic devices talk to a user space library that's called libimp. It's closed source. It speaks to the dev TXISP driver in the kernel space, which is also a closed source driver. And it understands how to communicate with the actual hardware in order to set up the device and the video streaming pipeline. In Linux, everything is a file for the most part. So all of your devices are exposed under the dev file tree node. And drivers you load as modules typically will show up there, and it's the driver's job then to translate system calls into various register writes, service interrupts, in this case moving buffers of video through direct memory access, managing clocks and power systems. So what we found then is when the drivers are closed, it kind of locks us into very specific things like specific Linux versions. And that's kind of the crux for a lot of my research on these devices has been around the image signal processing driver. I want to take a kind of a pause and say, if you haven't worked with drivers, maybe there's a chance you've worked with RESTful APIs. If so, this kind of an analogy slide to compare the concepts between web APIs and drivers at the I/O control level. Your endpoint would be like the example of tuning the image, various tuning parameters you might post to a RESTful API. In the driver world, you'll have in the driver basically a hex code that corresponds to that endpoint. So you're calling into the driver with a specific code and it will invoke that logic. Instead of using JSON in the HTTP body, you pass typically some kind of structure from user space, and the kernel driver will then look at the various struct members, and that will influence what it does. Your response then is the return code of 0 on success, or like invalid, or there's no resource on failure. The authentication, there is no cookie, JWT, API key. Instead, you're dealing entirely with files. These are your file descriptors and the permissions that they enforce. And the contract, there's no API, Swagger, docs. You're typically dealing with some kind of header if the vendor shipped one. So looking at a specific example then of a driver ioctyl, in this driver you have a frame channel ioctyl. You may have your primary stream as a higher resolution and your substream is a lower resolution, each one of those being a frame channel. I alluded to this a moment ago, but a lot of these devices appear to be stuck on Linux 3.10 or 4.4, which is the same Linux that existed 15 to 20 years ago. The rationale for this is there's tends to be a lot of interesting algorithms in the image tuning space. And when the vendor ships a closed driver, it's statically linked to the kernel structures in the version you're on. So to get past that version, you kind of need to do one of a few things. You can shim and try and stub out where those kernel structures are different, which is also very hard, and you still are left with a closed source driver that you've basically patched parts out of. The alternative is to try and reverse engineer the actual binary assembly driver back to C code so that you can then modify it and get to a mainline kernel and set it free. So that brings me to this project that I started a little over a year ago, which is the OpenTX ISP driver for these cameras. The process has kind of been to take the same existing working system, a Linux 3.10 with the user space library, and compile a separate driver and load it and see if it will work. Over time, for a long time, this is what we got. Maybe a few months into the project, a single solid green stream, no sensor data. And then last fall, there were some interrupts. We finally saw interrupts come through the open driver, but it was still just a green stream. It wasn't until I saw the interrupts that I even believed that we would ever get to the next slide, which is actual sensor data coming over the open driver. Doesn't look like what you would expect a security camera to, but it is real sensor data. That had to be picked apart then by implementing the image tuning pipeline. There are many different tuning bits, and as it turns out, it's kind of challenging to get everything totally right. This is probably one of the closer images to what a totally right image would look like. The methodology here then, you have some kind of program that's a decompiler like Binary Ninja or Ghidra. You take a model context protocol tooling that can communicate and pull the decompiled code from the decompiler and then kind of feed it into your LLM and ask it to derive you working C code. This is a little bit of a process, and it doesn't always work the way you'd expect. LLMs do hallucinate. One thing I found, it was a very double-edged sword to write a tracer driver. What a tracer driver does is it looks at all of the memory space, and it tries to basically detect any time a memory value changes and print out that that change occurred. When you first write a tracer driver, there are a lot of noise, and you kind of got to limit down to the memory ranges that actually matter. What I found though is when you feed these traces into an LLM, it gets confused and it thinks that it can implement them through side effect by directly writing the traces back to the hardware. This isn't really how hardware works. You may write specific keys or writes to specific registers, and then the state machine will manipulate memory internal to the hardware. You cannot just achieve device activation by emulating the writes that you see in memory. So the image signal processing pipeline, here's an example. At one end, you have your sensor, and it outputs raw Bayer video data over I2C to the SOC. And then the SOC has an image processing pipeline that will enhance, sharpen, do various things to the color, and ultimately transform the image to a YUV or NV12 compliant frame that can be streamed over an H.264 encoder. Reverse engineering kernel modules, and we'll look at this more real time towards the end. I found the two tools I used the most were Binary Ninja and Ghidra. Binary Ninja is a paid tool. The price point for personal edition, non-commercial, is somewhat reasonable, and it does a better job with MIPS instruction codes to extract back out the actual parameters that are passed into the C method. Ghidra is a free NSA blessed decompiler. It also supports MIPS. I just found that some of the functions were not able to be extracted as accurately, and that impacted the downstream work. SmartDiff is an open source semantic diff tool for source code and binaries. It has some MCP tooling as well for communicating with Ghidra and Binary Ninja. So if we look at the current status, you saw those images. The OpenTX ISP driver is mostly working. However, there are still some tuning bits that I keep disabled in order to not have it corrupt the image. Ultimately, would like to get total parity between that and the OEM driver, and then resume the mainline kernel port. This whole process has been very human in the loop. You know, when AI started, you would go to the web and you would type into a web prompt and get back a chat response. And maybe you would take that code and you would try and paste it in and compile it and see that it wouldn't compile. And then later on, it became more in the editor, right? You're making calls and it's editing code, and then like it got better at compiling code, and that kind of it brings us more to where we are today, where it becomes more possible to write frameworks around trying to automate the decompilation and get back to the original. This kind of brings us to our final chapter on secure boot implementations. Some of these devices have what's known as secure boot. This is where the OEM will sign the SOC with a secret key, and if you don't know the secret key, you won't be able to sign your own firmware, and the SOC will refuse to run it. A lot of computers and normal devices have secure boot, and it gives you control and security, but in the embedded world, this kind of ends up becoming to mean like what software can you run on the device is only what the manufacturer produces. How does that work? Well, at the core of it all are what's known as one-time programmable fuses. So inside of the silicone on the chip, you have these fuses that are just baked into the silicone, and at the time of manufacture, the ODM can choose to blow certain fuse bits, and it's irreversible. So the one on the left is not blown, the one on the right is. These bits can signify different things, such as secure boots enabled, whether or not you can use JTAG. There's all kinds of things. Before we go any further, I do want to point out that secure boot can exist for good reasons. I'm not sure that the $15 security camera that you choose to install on your house is a good reason, but that semi driving down the road with a video system that helps control its stopping distance, that's a safety critical system and no one should be tampering with that. So it's been a few years of studying secure boot bypass techniques. In 2023, I was inspired by Cristoforo Mune's talk on using electromagnetics to glitch OTP data transfers. It's a great talk. I definitely recommend you can find it on YouTube if you're interested in this topic. He demonstrates an entire automation around using an FPGA board to essentially blast the sock with electromagnetics at different points along the X, Y, and Z while powering it on. And what he finds is while it's not consistently obtained, it's easy enough to obtain via a glitch to bypass the secure boot enough to study the device. That didn't really fit my use case because I wanted to be able to buy a really good camera sensor, one that was secure boot, and run my own software on it consistently. So I learned about the sock swap, which I would say is kind of a caveman approach to doing things. You take the original camera that has a chip on it, and you blow hot air on it until it gets hot enough that you take tweezers and you pull the chip off. Now, it's really important that you don't knock any of these capacitors or resistors or anything else off the board, or it will not boot. I've done this. This is an example of where I put the chip back on, and it worked. Hooray. Pretty much every device that I've attempted, I had to spend 2 or 3 of that model just to get the hang of it. Not a scalable approach, but it does work, and once you've replaced the sock, you're good to go. There's still the question of if you can find the replacement sock. I would say there are some cameras, such as those flock cameras, where you may not be able to find the actual replacement sock. So what has been the reward for helping LLMs train over all these years on getting better at reverse engineering things? We're sorry, we're unable to process that request. Wow. So LLMs are putting up the guardrails now, and they're starting to say like, hey, we may have trained on the entire world's IP material, but we don't want you to reverse engineer a single driver, and we definitely don't want you talking about secure boot at a conference. This was me asking it last night if it could just update some of the information in these later slides to be more accurate, and it told me no. Fortunately, though, I bought a Blackwell RTX 6000 card a couple of weeks ago, and I've been using Quen now locally. Quen doesn't like to say no. It kind of just does what you want it to. Which brings us to the big finding on these Ingenia cams, okay? So this is, we did sock swaps. What if I told you that you can implement secure boot and possibly do it incorrectly? Well, in order to determine whether or not you did it correctly, you need to be able to extract from the sock what is known as the boot ROM. The boot ROM is infused in the chip at the time of manufacture. It contains code, and it can't be modified. It's different from flash ROM. It's just burnt into the chip. Well, I was working on something entirely unrelated some months ago when my co-researcher messages me around midnight with just a file. It said like t31bootrom.bin. I was like, huh, that's interesting. And then another file came through. It said t41bootrom.bin. I was like, all right, I think I'm going to switch and change what I'm doing right now. And I loaded these up in Binary Ninja, and I went to my LLMs and I started asking. I said, do you see any problems with this implementation? And the reason I would ask an LLM and not just answer it myself is it's raw assembly. And you'll see in the dissembler, a lot of methods just like submethod 0002, submethod 0003. And to trace through this would take a really long time. Well, the LM started to respond. The cryptography looks really well sound. I was like, oh, that's not good. And then it got to a certain method on the T31, and it said, wait a minute. And then it spun some more and some more and some more. And what I got to was that the cryptography was actually fully implemented. But when it got to comparing the key, it was only comparing the first word of the key. Like, well, that's pretty interesting, because if you want to brute force something and you don't have to derive the entire full key, you just have to get the first word right, that feels a lot easier. We'll come back to that. So then the newer devices, I started analyzing those boot ROMs. And I said, hey, do these boot ROMs have the same problem of only checking the first word? Sometime later I got my answer, no, they fixed that. And I was like, damn. And then it was like, but it seems like there's something else to check. The init table, okay? So those single one-time programming fuses that specify whether secure boot's enabled, they have to be verified. The init table gets loaded into SRAM from the fuses, verified by the software, and then progresses. Well, what if you could just manipulate the SRAM and turn it back off? And that's what we did. We wrote a simple Python script that patched the exact bit or byte of the firmware, and it basically reads the fuses, says secure boot's on, the bootloader runs a little bit more, encounters an instruction, says secure boot's off, and then it boots whatever you want. Cool. The second one's actually easier to implement than the first one. The first one, you actually have to brute force something, and that's what this slide is about, is basically the search rate. It took about a couple minutes to brute force the first byte of that word, and then we were able to boot whatever we wanted. Well, this works out great because for 3 years we had been working on open source firmware and we had been swapping the socks on the secure boot ones, so now we have a method to just put what we want without swapping the sock. I alluded to this, the newer ones, they fixed the crypto and then they introduced a different problem. So before we get into the demo, I do want to say I tried very, very hard to disclose this. I contacted the manufacturer, I contacted the ODMs, I contacted the downstream device vendors. One of the vendors fairly responded. They weren't totally happy about this. It also wasn't their fault. It was the manufacturer. The manufacturer hasn't been super responsive. The CVEs haven't been responded to or allocated through the CVE process. I'm not entirely surprised, given every other Linux vulnerability that has cropped up over the last couple months, that they've been totally inundated by these type of vulnerability reports, and probably this one of being able to run what you want on your own physical device ranked a little lower on their list of priorities. Given all that, I think that's enough material that we should just spend the rest of the time on some live demo and taking some questions. Also want to thank all of you all for coming, besides my parents, my brother, and my dog Goulash. But I am gonna show you all some demos and let you ask questions if you have any. For starters, so I have Binary Ninja running. The screen resolution isn't totally great on this projector, but you can kind of get a sense. For the ISP driver, everything you see here on the left is a symbol, a different function, and this is kind of what I was talking about with these sub-functions. Like you'll see in the actual boot ROM code, if you were to look at it, a bunch of like sub-functions. This is a high-level interpretation of assembly. You can go down to the actual disassembly code, the low-level IL, medium level. I think once you hit high level, this is as good as it gets. If you go to pseudo C code, it's approximately good, but it loses representation over the actual assembly. This is the smart diff tooling, so this gives an MCP tool into that program. And I should be able to go over here and ask some questions. Let's see here. And this is going to be using my local Blackwell card that's at my house through the VPN. Let's see. Computer use plugin was declined. Okay. I have a couple other demos. So one, we're going to hook up this development board, which is a teacup development board that we made specifically for these Nginx socks. And I used the caveman approach to take a secure boot chip from a vendor camera and put it onto this board so that we could demonstrate bypassing a secure boot. So what we got going is there are two flash chips on this board with a little switch that I can toggle between them. Let me get my screen session going and plug this in and see some activity. Okay, so this is just the cameras booting the normal vendor firmware. You get to here and you don't know the password to log in. That's pretty typical experience over UART with these type of vendor cameras. If I were to switch chips back and reset this, I believe what I have flashed on here now, it simply won't boot because it's our standard image for this camera. If I unplug, plug it in, you see nothing. This is the sock rejecting booting something because the secure boot's enabled. In order to get past that, I need to, and this is where I referenced that cloner mode earlier, we're going to use it. The idea here is you short pins 5 and 6 on the flash chip while you plug it in so that the device can't read from the flash. It defaults to its bootloader mode. My might take a couple tries. We'll see. So if I go over here. I gotta remember which terminal this was supposed to be in. Okay, so I didn't find it because I didn't do a good job. Give it a couple tries. If I don't get it live, I will be publishing the actual bypass scripts later today. These only pertain to the Ingenic devices. Every sock is a little bit different. I guess I would say, like, are there any questions at this point? I know some of the material is a little higher level. Just shout out if you want to know something. I see. In that particular case, right, so the driver's less than 2 megs. It is a very deterministic problem that if a driver exists that can initialize and stream, it is theoretically possible to arrive at the open source driver. So I just believed very strongly that it would be possible to reverse engineer the protocol and the hardware initialization processes. That was the hardest part, really. Once we saw any sensor data at all, then it was just like work ahead. It wasn't like a total wall like that. But I mean, it is frustrating, right? Like when you work in industry and you're doing like 2 or 3 week sprints, and something always has to be delivered in that cadence. I mean, you would never go to your manager and say, well, I'm gonna need a year to maybe 2 years to do this project. Like, industry just doesn't work that way. But that's not to say that that mentality can't ever work. What isn't working is the way that this plastic is making it hard for me to shut the chip. I was able to do it in the green room. I'll give it a couple more. What I want to write is the tcup backup d.bin. It's not going to find the device. Any other questions before I totally wrap up and get off stage for the next person?
You said you reached out and seen the vendors.
Yeah.
Is this your first public disclosure?
Yeah, I've never encountered a vulnerability that was anything like this before. So yeah, it's my first one.
Is this also the first year or
No, I disclosed it a little over 2 months ago. Oh, okay, we found it. I finally did it right, and I just gotta flash it and show you it boots, and we'll be on. So this actually is a command line program that we wrote by reverse engineering that cloner protocol. There's this Chinese GUI that's just terrible and hard to use, and it was just easier to sniff out the USB traffic and reverse engineer it than to continue using that GUI. So if we were to look at the UART side of things, you can see this is actually over UART, the bootloader from the SOC, and it's saying like it's erasing the chip right now. And then now it's going into a waiting to receive, and then now it's going to start writing the firmware here. And this is actually a lot faster than the clip programmer method. The USB cloner protocol is a lot faster. About halfway. While that finishes writing, I'll just show you. I'd asked local Quen before this to basically compare those two images, the one that wouldn't boot with the one that would. This is a 1 byte difference. All right, we are fully flashed. I should be able to unplug, plug it in, and look at that. We are booting up Theano Linux on a secure boot device without knowing the signing key. And then you would see with the Wi-Fi, there's probably, no, actually I don't think these have Wi-Fi chips. But anyway, thank you so much.